Okay, hi. First, I'd like to thank the organizers for the opportunity to give this talk and also for bringing this nice workshop to Natal. Um, Here's the outline of my talk. I'm basically going to talk about time-dependent correlations, local correlations, and I'm going to start with some motivation about how the dynamics can be different in the bulk or at the boundary of one-dimensional systems. And then I'm going to describe some effective field theory that captures the long-time dynamics, which is not captured by usual CFT. I'm going to discuss the difference between integrable and non-integrable models for autocorrelations at the boundary. And here and there, I'll show some numerics, some time-dependent DMRG to compare with the theory. And the most recent work about boundary autocorrelations was done in collaboration with Sebas Aliens, who is finishing up his PhD in Amsterdam. Flavia Ramos is a PhD student in Uberlândia, working with José Cândido Xavier. Okay, so these are the quantities we're going to talk about. So consider we have a semi-infinite one-dimensional system with a reflective boundary at the origin. This could be a lattice or a continuum. I'm going to focus on lattice models. And consider that we have some gapless Hamiltonian that describes the interactions here in this chain with some ground state size 0. And we're going to be interested in some local operators that act on some site J or a finite number of sites. And we want to compute the autocorrelation, which depends both on time and on the position of site J on this chain here. So we're interested in what is the difference for this autocorrelation when we are sitting right at the boundary versus in the bulk of the 1D chain. And most of the results will be about spin chains. So I'm going to use the XXZ chain, which is integrable. So that's nice. We're going to use that. And I'm going to focus on the gapless phase where delta, the anisotropy parameter, is between 0 and 1. And some correlations of interest here would be the longitudinal spin autocorrelation that involves the SZ component of the spin operator, and the transverse spin autocorrelation that involves the Xn or Y components, or here S plus, S minus. Actually, the simplest example that I'm going to use to illustrate the main ideas is the spinless fermion version of the XXZ chain. And in that case, here I'm going to focus on repulsive interactions between fermions. V here is essentially the same as delta in the previous slide. It is exactly the same as delta. In this case, we can talk about the spinless fermion Green's function, which is defined here, and how it varies between boundary and the bulk again. And the anti-commutator here is convenient in some cases, but it's not crucial. Basically, this would be single particle or single hole propagators of the spinless fermion. Why would we be interested in the physics of this kind of quantity? Traditionally, in condensed matter physics, most of the experimental probes of dynamics work in the frequency domain, and there the connection is that if you take some Fourier transform of, say, these local Green's functions, you get the so-called local density of states. There has been a lot of work on the local density of states for 1D systems. There is a prediction from conformal field theory or from Luttinger liquid theory that predicts the low frequency behavior, because if you know from Luttinger liquid theory that the Green's function decays as some power law with some exponent that depends on interactions. Here I'm quoting the results for spinless fermions where k is the Luttinger parameter and k is 1 for free fermions. If G decays as a power law, you can predict that the local density of states is going to scale as some frequency to some exponent alpha that depends on the position on where you measure the local density of states. So it's different between J at the boundary or the chain end or J in the bulk. And for free fermions, this alpha is just 0, so the local density of states for free fermions is constant. But if you have repulsive interactions, alpha is positive, so you can predict that you're going to have some suppression of the local density of states with some exponents that are related by a single parameter, the Luttinger parameter. And this has actually been used back in the 90s as a test of Luttinger liquid behavior, for instance, in carbon nanotubes, because if you see in some tunneling experiments some power law dependence with frequency or temperature, say you measure it in the bulk, you can fix the Luttinger parameter, then you can predict that you should see also power law behavior at the boundary, but with a different exponent that you have already fixed. Sorry. So that was in the frequency domain, but I'm going to mainly focus on the time domain here. And recently the focus has kind of switched to the time domain, basically motivated by experiments in cold atomic gases, because now people can manipulate many-body states and Hamiltonians in real time. So you can measure things directly in time. And quite often this discussion is done for non-equilibrium states, but we can also talk about equilibrium dynamics in real time. And for instance, there has been this proposal that one can measure equilibrium time-dependent spin correlations using this technique called many-body Ramsey interferometry. So basically, you shine some sequence of laser pulses and measure some local spins after the system has evolved in time. So I want to compare bulk and boundary, but first let me just tell you what happens for autocorrelations in the bulk, and then later we'll bring back the boundary. So let's talk about my example of spinless fermions in the infinite chain. So again, I have some site J here, and in this case, I'm talking about the thermodynamic limit, so I have translational invariance. The spinless fermion Green's function does not depend on site J because of translational invariance. But let me add some spatial dependence here just by saying that this C and C dagger operator is here. I'm choosing just some whole part of the Green's function that is the whole propagator. So let's say that the C and C dagger act on different positions, also a different time, so some time t. So what is the result here? Let's start with the simplest case of free fermions. And in that case, we just have this tight binding Hamiltonian. We can calculate everything exactly. And this is, the whole propagator is just given by this integral here. And usually, if you're interested in the large distance asymptotics, what we do is we say, well, we don't need the entire spectrum. Let's just focus on low energy excitations about the Fermi points of this dispersion at kf or minus kf, and here I'm working at half filling, kf is pi over 2, and from that you can describe the large distance asymptotics just by linearizing the dispersion, and you get the prediction from just scaling, or that's the CFT prediction. But here we're also interested in the time dependence. And here there is another important contribution that comes in, and the thing is that this integral here has some saddle point contribution that comes from the condition of minimizing the argument of the exponential here, and this is the condition that you're going to get some saddle point at some value of k such that the sign of k is x over t. And this has a solution whenever x is less than t. So this is deep inside the light, inside the light cone. So the picture is like this. So if you're working at equal time correlations, you can always use CFT to describe the large distance asymptotics. But if you're interested in correlations inside the light cone, you have to take into account the saddle point contributions. And what they do is that they introduce some contributions from Ks, here Ks away from the Fermi points, so at finite energies, and that implies some oscillations in real time. So in particular here, I'm going to be interested in the autocorrelation, so x equals 0, so how the autocorrelation decays with time, so along this direction here. And in that case, when x is 0, the solution is that sine of k is 0, so for the whole, this is k equals 0 here at the band edge, or the bottom of the spinless fermion band. For the particle, that would be at the top here at k equals pi, so you have a saddle point contribution. And in that case, you have this saddle point contribution from a region in momentum space where the dispersion is approximately parabolic. And that changes the rules, because now we know that a particle with a parabolic dispersion has a propagator that decays as 1 over time, which is slower than the contribution from the Fermi points with linear dispersion. So just to be clear, this is the cut of the real part of the whole Green's function as a function of time. And you see that there are some oscillations, and the frequency here is 1, is the energy of this deep hole at the band bottom. And the decay here is very slow, with exponent 1/2 for free fermions. And again, it's I should say that there is also one contribution from the CFT prediction, but it's much smaller, and you cannot even see it here on this picture, the non-oscillating contribution. Okay, so that was the free fermion case, and this picture is useful because now we can add interactions on top of this picture. This picture tells us that if you want to describe the long-time dynamics, we, again, don't need the entire spectrum, but it's not sufficient to focus on low energy contributions. But we can take the Fermi points, contributions from the Fermi points to define the usual right and left movers in this mode expansion. But also here, we need the hole at the bottom of the band, k equals 0, and the states of particles at the top of this band at k near pi. And this kind of idea was pioneered by the group of Leonid Glasman. We used the same idea for spin chains. And basically the idea now is that you have to use this modified mode expansion and include in the effective field theory all interactions between the low energy modes and these high energy excitations at the band edges. And here you can include all the marginal operators that are allowed by symmetry. The effective Hamiltonian comes out like this. And this is known, well, it can be called an effective mobile impurity model because it appears in other contexts in condensed matter system. Basically, the idea is that now we're allowing for the possibility that the operators that we're applying on the ground state can excite a single hole at the band bottom or a single particle at the top. But after these high energy excitations are created, you cannot create any more excitations with high energies, but they can interact with the low energy modes. So we have a particle number constraint for this high energy excitation, say just one deep hole that is coupled to the low energy modes that are described by usual latent liquid theory after bosonization. And the physics that appears here is that now we're going to compute correlations that involve these impurity fields or D fields, high energy modes, and they're coupled to the low energy modes. They can shake up the Fermi points. This is the usual X-ray edge problem. So, and this is how we're going to get the exponents for the long time decay from this kind of theory. This coupling here can be handled analytically. And this is the result for the interacting case. Here I'm writing the low energy contribution for the whole Green's function with the exponents I had before. Also this high energy contribution that comes from exciting the band edge mode. So now I'm going to have some frequency epsilon that determines the frequency of the oscillations in real time. The exponent alpha depends on that coupling gamma between the high energy modes and the low energy modes. And we can predict, yeah, so you can write this exponent in terms of this coupling gamma and the Luttinger parameter, which is a property of the low energy spectrum. And since we're working with the integral model, it's nice that we can fix these parameters. So the Luttinger parameter is known for the XXZ chain. Here is a function of V or delta. And the new information here is that we also need some information about the high energy spectrum. So we need the energy epsilon of this hole at the bottom of the spectrum, and we need this parameter gamma here that controls the coupling and controls the exponents. And the way to determine gamma, like I said, this is very similar to X-ray edge physics. So this gamma can be interpreted as some kind of phase shift. If we compute the finite size spectrum in the field theory and in the Bethe ansatz, when you create this deep hole inside the ground state, you can relate gamma to the so-called shift function, which is some kind of dressed phase shift, and you can compute this exactly for the XXZ chain at zero field. So it comes out as a very simple function of the Luttinger parameter as well. So it vanishes at the free fermion point, gamma equals 0, but in general it's going to depend linearly on the Luttinger parameter. So all this gamma, epsilon, they're all fixed here. And that was for the Green's function. We can also play the same tricks for the XXZ chain. Basically, what we need is just the Jordan-Wigner transformation to write down the operators in terms of spinless fermions, allow for the possibility that some of these fermions will be excited at the band edge modes, and some will be low energy modes. And then we can work out what the exponents will be for the long time decay. And here I'm writing down the result for the longitudinal spin autocorrelation at long times. And these are the low energy contributions that come from CFT. Actually, these C and D are prefactors that are known exactly from the work of Luciano. And these are the high energy contributions. Here I'm calling one impurity when I have, say, just one hole at the bottom. But there's also one contribution because the SZ operator is basically the density of fermions, so you can create a particle-hole excitation, and both the particle and the hole can be at high energies. So there is a contribution of 2 high-energy modes that oscillates with twice the frequency here, with some exponent that is not too interesting, actually. So the main contribution to the long-time decay of the XXZ chain in the bulk would be this term here, where K varies along the as a function of delta like this. And this kind of prediction has been checked against numerics and time-dependent density matrix renormalization group results. And also, usually this kind of approach goes under the name of nonlinear Luttinger liquid theory because it includes these modes with nonlinear dispersion. For the Bose-Gas, at least, or the Lieb-Lininger model, there are some exact calculations by Kitanin and collaborators for the long-time behavior of correlation functions that agrees with the predictions of this nonlinear Luttinger liquid theory. Okay, so let's go back to the topic of this talk. We want to discuss what happens for the open chain. So again, here I'm going to consider some site J, where J is the distance from the open boundary. And we want to talk about the time dependence of this autocorrelation of our Green's function. And when you talk about the time evolution here, there are some important time scales. It's important that when you apply some operator at site J, and as a function of time, there will be this light cone that opens up above the position J. These are the lines here where the velocity of the light cone, or the velocity, maximum velocity of the particles, here the same as the low energy velocity of the Luttinger liquid theory. And at some time, this light cone will hit the boundary, and then it will reflect back. And you expect that if you're sitting here and measuring the autocorrelation function, you will notice the presence of the boundary when this wavefront is reflected and reaches back your position here at this, I'm going to call it reflection time, which is 2 J divided by velocity. And again, let's consider the simplest case of free fermions now with an open boundary. And in this case, again, we know the exact spectrum, just a cosine band, where K is only positive now. And the wave function of the exact eigenstates has this sign dependence. J to n, if you like, but to infinity. I'm taking, yeah, it's semi-infinite. So. Yes, so and then I'm integrating over K because I'm considering really the semi-infinite chain. And then in this case, so again, this is the equivalent expression for the open chain, equivalent to the expression I showed before for the case without boundaries. And this is the local density of states, which now depends explicitly on the position where you measure the density of states. You can plot this. So this is G, or the real part of this. I think I defined it to be real. So it's already real. So this is G as a function of the position J, where you measure the Green's function, and as a function of time. And you see here, there's a very clear change of behavior between below and above this line. This is the reflection time that I defined before. It's 2 times J divided by velocity, and velocity here is 1. So below this line, you see that the Green's function, the local Green's function does not depend on J. So this is the kind of behavior I'm going to call bulk behavior, because it's like we have translational invariance here again. We don't know about the boundary until the wave reflected at the boundary comes back. So the bulk behavior is going to be here, J far from the boundary at long times, that's what we're interested in, but below this reflection time. And on the other hand, we are also interested at what happens at the boundary. Sorry? In the ground state, yes, exactly. Yeah. We can also talk about the finite temperature case. I think Jesko is going to talk about the finite temperature next week. Yeah. So you can do equilibrium at finite temperature. But today, everything is ground state. Yes. So yeah, we can also sit here at the boundary and look at how the Green's function decays as a function of time. And this is just the cuts of the Green's function right at the boundary as a function of time, and here in the bulk. And these are the local density of states. So here, first, the result in the bulk is equivalent to what I showed before. So there is some oscillations and slow decay. The local density of states has some Van Hove singularity at these band edge modes, or the dispersion is parabolic. And that's what controls the exponent of the decay in real time here in the bulk. On the other hand, at the boundary, there is a suppression here of the local density of states at the maximum or energies, or at the band edges. And this is essentially because of these factors here of the sign in the integrals that tell you that the wave function of the eigenstates for a small k or k equals to pi vanish at the boundary. Or vanish at the boundary always, but for k equals going to 0, it's going to be suppressed. And because this is suppressed now, as opposed to the Van Hove singularity, you see there is some faster decay in time. So this is actually quite general for other autocorrelations, that at the boundary, we're going to see oscillations, just like in the bulk, but the decay is going to be faster at the boundary. And how do we describe this? How do you get the equivalent exponents for the long time decay? So once again, I'm going to use this mode expansion that includes the band edge modes at k equals 0 or k equals pi. This is the fermionic field now, defining the continuum limit. And we impose an open boundary condition that the fermion field vanishes at the boundary, x equals 0. And to get this condition to be satisfied, the usual trick to treat the low energy modes is to use this folding trick, where this condition imposes that right and left mover here are not independent, basically because a left mover comes in and is reflected at the boundary. So we can define left movers to be the continuation of right movers to the negative x positions, and then we will work with a single chiral fermion defined on the infinite line. And so this is the condition for the fermions. There is an equivalent condition for the bosons after you bosonize. And for the high energy modes, they're independent, so I really need this condition that the high energy fields vanish at the boundary, the D and D bar, particle or whole. And what this implies is that whenever you calculate correlation functions that involve this field, high energy mode at the boundary, you cannot take D of 0, you have to take D at the short distance cutoff, like the first site of the lattice, the lattice spacing. And if you expand this is the derivative of the high energy field at position 0, which is not 0. And the simple observation here already tells you that we get an extra derivative for the high energy mode at the boundary, which for the time dependence implies that in general, this operator has higher scaling dimensions, so the exponent for the long time decay will be larger at the boundary than in the bulk. And here is the version of the mobile impurity model when you have open boundary conditions. So the difference from what I showed before is that now I have a single chiral boson. here I wrote only one D, but there's also D bar with an equivalent dispersion, quadratic dispersion, these band edge modes. And here D, again, the high energy modes are coupled to the bosonic fields that describe the low energy excitations in the usual Luttinger liquid theory. And plus irrelevant operators. So these are marginal operators. And it's important here that I'm using the same epsilon, the same energy of this band edge mode, and the same gamma, the same coupling or phase shift as we used in the bulk. So if you like, this is just like taking the mobile impurity model in the infinite chain and folding it to the semi-infinite line with the same parameters. And so here are some results. Again, it comes from computing correlation functions of those fields that include high energy modes. For the single Fermi-Green function, we have the oscillating part and the low energy part, which is non-oscillating. These are the exponents that are predicted from Luttinger liquid theory as a function of the Luttinger parameter. And these are the high energy exponents that controls the decay of the oscillations. So they are, again, different in the bulk or at the chain end, the boundary, but they both depend on the same parameters, the Luttinger parameter and this phase shift gamma. And one thing you notice is that here the exponent at the end is already large. Even if you take gamma equals 0, which is 3 fermions, the exponent at the end is going to be larger than the exponent in the bulk. So it changes abruptly by +1 as we go from bulk to end. Also, there are different factors of 2 here in the interaction-dependent corrections. And this comes from the fact that basically it's a result of the folding trick. That we have factors of 2 coming from the number of bosons. Before we had right and left, now we have only a single chiral boson. Put in factors of 2. The correction to the exponent that comes from interaction is larger for the boundary case than for the bulk case by a factor of 2. And these are the results for the XXZ spin chain, how the longitudinal or transverse spin correlation functions decay in the bulk or in the boundary. So here I'm putting everything together. Parallel is longitudinal and is perpendicular is transverse. And here, to simplify the expressions, I use the fact that we can fix the parameter gamma, the phase shift, from the shift function as a function of k as well. So we write all the exponents as functions of k. Here on this side, there we have the high energy exponents for longitudinal or transverse, and those are the low energy ones. And you can do here is that, say, for the Heisenberg chain, delta equals 1, k is 1/2. So all these exponents, the exponents that are labeled parallel should be the same as perpendicular, but they are not the same between bulk and boundary. So for instance, here, for example, if you take, set k equals 1/2, then they becomes the same as the high energy and low energy exponents. I should say bar is always high energy, no bar is low energy. Here, set k equals 1/2. This is 2, is the same as the result from the low energy contribution. But in general, k is going to be larger than 1/2 along the XXZ line with delta greater than 0. So at the boundary, the high energy contributions decay faster than the low energy contribution. And recall it's also the other way around for the bulk. No, I don't have any simple way of understanding. Yeah, like this. Yeah. Yeah. No, I don't have a good rule to describe this. A rule of thumb. Okay, so we can also do fermions with spin. So this is Hubbard, away from half filling at zero magnetic field. So the equivalent mobile impurity model for when you have fermions with spin was worked out in these papers. And there, the idea is that now you have spin charge separation, and you have these band edges both for spinons and for holons. And usually when you have fermions with repulsive interaction, the band edge of spinons lies lower than for holons, and that's the band edge that controls, it gives the most important contribution to the long time behavior. So this would be the Green's function for, say, spin-up fermions. The prediction is that it's going to oscillate with some frequency that is given by the band edge of the spinon dispersion, and it decays with some exponents that, again, are different between bulk and boundary. And here we have used that this is zero magnetic field, so we can use the SU2 symmetry in the spin sector to fix a lot of parameters. And at the end, the exponents depend only on the Luttinger parameter of the charge sector. And this phase shift, this is the phase shift for scattering between these high energy spinon and low energy holons. So these are some numerical results. So the method we used, Xavier uses, is this so-called adaptive time-dependent DMRG, which does the simulation directly in real time for finite chains. And there are some limitations both in finite size and finite time for how long you can run the simulation. But basically, the idea is that, okay, so the dots here are the numerical results, and the red lines are fits to the expressions I showed you before. Yeah, so the important point here is that all these are longitudinal on the top, and transverse spin autocorrelations. And the important point is that they're all fixed by the same parameter in those expressions. And this is the result of fitting with this parameter as a free parameter. This is called psi here. And that's compared to the exact prediction of what it should be. And W here is the frequency of the oscillation that should correspond to the band edge mode. So for the frequency, you get very good accuracy, and there is agreement between the frequency of the oscillations in the bulk and at the boundary. For the exponents, the agreement is better for a smaller delta. It gets worse for a larger delta, but as usual, you can blame it on irrelevant operators that are not so irrelevant and give some corrections at finite times. But we tried a few different things. So for instance, if instead of allowing this parameter the exponent to be free, if we fix what the exponent is, we also get good agreement. And here in this curve, in this plot, there are two curves, one with the free exponent or fixed exponent. You have to zoom in to distinguish between them. So you can think that this is some kind of test of this nonlinear Luttinger liquid theory or mobile impurity model, kind of like the test that we had for Luttinger liquid theory at the beginning. You can predict different sets of exponents at the boundary or in the bulk, and they're fixed by the same parameters in the effective field theory. And here I've been talking about power law decay of these oscillations that come from high energy excitations. And then one important question is it really power law decay? Because here I'm talking about excitations that lie at high energies inside the continuum of some lower energy excitations with multiple, say, particle hole pairs. So usually when you have some high energy excitation in the continuum, you expect that whatever singularity or power law singularity you have inside the continuum is going to be broadened by decay processes, just like usual Fermi's golden rule. But here we are saying it's really some singularity at higher energies. And for the bulk case, we can make the case that it's actually a true power loss singularity. And this is protected by, let's say, kinematics, because basically the autocorrelation as a function of time can be obtained by some integrals over the dynamic response functions as a function of momentum and frequency. So if we know that the dynamical structure factor, for instance, has some true power loss singularity, the local frequency-dependent correlation is also going to have some power law singularity at finite energies. And then Fourier transform again, you get some power law decay in time. And for the dynamic structure factor, we know that there is a true power law singularity because there is a lower threshold here. This is a function of momentum and frequency. There's a lower threshold below which the spectral weight vanishes. So the support is really above this line. And since the spectral weight is going to turn on abruptly above this line, you expect to get some exponent here. So for the XXZ chain, for instance, this is usually some divergence with mu, negative mu here. And this is just from the simple fact that if you look at the spectrum of states with finite momentum, there will be some finite minimum energy that defines this threshold. For free frames, it's 0. It's a step edge. For Heisenberg, it's -1/2 with logarithmic corrections. Yeah, 0 to -1/2. Yes. Yeah, so for the bulk, you really expect this power law singularity, power law decay of this oscillating component in the autocorrelation functions. And it's just from simple kinematics. But at the boundary, you cannot use the same argument because that was based on momentum dependence. So if you don't have translational invariance and you're just sitting at the boundary, then I cannot use this argument. So why should I get power law decay of autocorrelation functions? And the truth is, in general, we should not expect that because in my theory, I have neglected some irrelevant operators, but you can also include some operators and look at that are in general allowed by symmetry and ask what they do to these high energy modes. So one thing they can do is, for instance, if you compute some self-energy of this high energy particle whole, you can get some non-zero decay rate, which is going to imply some broadening of the singularities in the frequency domain and exponential decay of the oscillating contributions in time. So we have analyzed a few irrelevant operators that are allowed by symmetry, and really the dangerous ones are the guys that do not conserve the number of these high energy modes. So now it's like you create this high energy hole, and it can cascade down, decay to a single hole at the Fermi surface, plus a large number of particle hole excitations. And in the bulk, this would not be allowed because it does not respect momentum conservation, but at the boundary it's allowed. And then you can generate some process like this, where you create or annihilate some high energy excitation, decaying into a high number, arbitrary number n of low energy particles and holes. So in general, yeah, the truth is we should expect that there's exponential decay of the boundary autocorrelation. But for the integral model, we don't see that. Here the belief is that in the integral model, we have some non-trivial conservation laws that somehow rule out, do the magic and rule out this kind of decay process from the effective field theory. And it's also important that this is really an argument based on the self-energy of these high-energy excitations. And the self-energy does two things together. The real part gives you some frequency shift. And if there is a frequency shift, we can predict that the frequency we see at the boundary is different than the frequency in the bulk. And together with that, there's the imaginary part of the self-energy. What it does is give the decay rate of the high-energy hole, and it gives the exponential decay. So if something like this happens, there are two things that you should observe. Different frequencies at the boundary of the bulk and exponential decay at the boundary. So we tested that kind of idea. So we wanted to look at some non-integrable spin chain to see that what happens at the boundary for the autocorrelation at the boundary. So we considered a non-integrable spin-1 chain with exchange anisotropy and single ion anisotropy. I don't have results for the integrable spin-1, sorry, just a non-integrable one. And here, the result is that the bulk autocorrelation is, I don't have the plot for the bulk one, but the bulk autocorrelation, you can really fit the oscillations decaying with a power law. And the frequency we get from the numerics agrees with some with the threshold of the dynamical structure factor. And so this is the dynamical structure factor for this spin 1 chain. It's gapless, yes. I should say this model is gapless in the negative delta regime. So, and as a function of the single ion isotropy, it's also there is some extended phase where it's critical. So it's gapless at the spectrum is gapless here at momentum q equals 0, but it's gapped at q equals pi. Yes. And so, yeah, from the numerics, we can read off some frequencies that agree with the expectation in the bulk. But if we look at the boundary autocorrelation, what we see is that, so this is the result at the boundary, it oscillates with a frequency that is clearly very different. So remember, we have very good resolution in the frequency. There's a lot of oscillations here. And the frequency you get, in this case, I think it lies somewhere in here. So it's no special value, no boundary of the, no threshold of the spectrum here. Also, we find some evidence for exponential decay of this correlation. So basically, if you try to fit this with a power law, here you see that the best fit with the power law, the red line overestimates the result, the numerical results, the black dots at longer times, which suggests that this is actually decaying faster than a power law. What we also did is that we can subtract off the power law contribution from the low energy modes, which is still there. In the case as t squared in this case, with some prefactor that we can fix from static correlations. So this is also fixed. Subtract that off and look at how this thing, what is left, decays as a function of time. So this is a log-log plot, and here the maximums are fit to the straight line. So some indication that the boundary autocorrelation of the non-integral spin chain decays exponentially with time, and also the frequency is different than in the bulk. Right. Yes. Yes, I agree. Yeah. So the first thing we thought was to do Babujan-Taktajan, or the Q deformation of that. Yeah, we can do it. Yeah, it's doable numerically. I just couldn't convince Xavier to do it. He focused on the thing on the next slide, but it's doable, and yeah, it's interesting as well. So you can add some parameters. We just picked one point in the phase diagram to look at it as an example of a non-integrable spin chain, or not one, a few points. Yeah. So something we're doing at the moment is that basically I jumped from integrable to non-integrable, but it would be nice to have some model where we can tune the integrability breaking. So one example would be just this. Just take the spin 1 model and play around with the parameters so you can control the integrability breaking. But what we are doing at the moment is the spin 1 half, go back to the spin 1 half case, but with second neighbor exchange interactions. This is the anisotropic zigzag chain, or J1, J2 chain. And there are some, we have some preliminary results, so like this plot here. This is boundary autocorrelation as a function of time for some values of delta, J1 and J2 in the critical phase. And somehow, surprisingly, what we find is that the frequency is this a non-integral model for non-zero J2 and non-zero J1. But what we find is actually the frequency at the boundary is the same as in the bulk, what we didn't expect for a non-integral model. And also, it looks like this decay for the non-integral model can be fit to a power law. So I don't understand this. The possible explanation is somehow the coupling constants of those irrelevant operators that give the decay rate of the high energy modes is very small. But yes. Uh-huh. Yeah. From Hubbard. But you got second neighbor couplings, or the same chain? Same neighbor. Yeah, so here I have second neighbor. That's exactly the point. Yes, yes. So you have a. Oh, that's right. You told me this before. Yes. Fair. Yeah, another possibility. Actually, that's also in our list because then you can have three spin interactions and some special points with J1, J2, and the coupling by a single parameter. But yes, yeah, so that's also doable. Yeah, um, yes. So and I talked only about the case of open boundary conditions because it's easier. But in principle, this kind of effective field theory for the long-time dynamics can be generalized to other kinds of boundary conditions. Maybe some interesting integrable ones with fields at the boundary and or boundary bound states and things like that. We haven't done anything about that yet. And of course, a very tall order would be to have some exact calculation of boundary autocorrelations. Yeah, so something comparable to some recent progress in the calculation of uh, correlation functions from the form factor approach without the boundary that recover results for the large distance asymptotics from CFT. But as far as I know, there are no results for the long time asymptotics. And to conclude, I told you that if in general, if you take a critical one-dimensional model and you look at correlations inside the light cone, you're going to see these oscillations as a function of time. And this long-time behavior can be predicted by an effective field theory that is not just the standard Luttinger liquid theory or the CFT, but it also has to include these band edge modes. And for the XXZ chain, we showed that these boundary autocorrelations oscillate with the same frequency in the bulk or at the boundary. This is kind of expected from the Bethe-Ansatz solution of the open chain or the infinite chain. You get the spectrum that has the same band edge. But the exponents of the parallel decay is different between bulk and the boundary. You can predict what they are, and they are related by a single parameter. And more generally, if you consider non-integral models, the boundary autocorrelation is going to be sensitive to the integrability breaking, that you're going to get some exponential decay in time. So I think that's all. Thank you.